So who was super confused this week? Yay! Thank you for being honest. Okay. So I am going to try to unconfuse you this week. The thing that I think is more important than just plowing on and learning new stuff is to figure out how does the new stuff that we're learning apply to what we already know. Okay? Because really that's all about life. You have basic building blocks and we're just going to keep building them together. So if we have a firm foundation, we can add things on top of it. If you're in algebra, the things that you're learning in algebra now are building upon the things that you knew in regular, like middle school and elementary math, okay? The things that you learn in Algebra 2 will build upon the same things that you learn in Algebra 1. However, they're all still the very basic building blocks of the order of operations. Like we learned that in like third grade, third and fourth grade. So same thing with the science this week. We're going to take it a little slow, and I'm going to try to just break down. I'm not going to repeat or read word for word from the book, but just kind of take the whole concepts that they discussed in the book, and we're going to break it down. How does it apply to what we already know? How can we take what we already know, apply, ask new questions, get new answers, and then move forward, and then we're going to have a little bit of math. And I will say that your book does some of the math things a little different than I would do them. And because you happen to also have an Algebra 2 teacher for your physical science, I'm going to teach you math version of that. Because personally, I feel like it makes more sense. So then you'll have two options. You can do it the book way, or you can do it my mathematical way. All right? So last week we finished up elements, and you guys did great on your presentations. So I'm going to step back again. We're going to go back to Module 2. So at the very beginning, so we learned all about science, and then Module 2, we started classifying matter, correct? Remember at the end of Module 2, we had that huge slide that had all of the different arrows and all of the different ways that you guys had learned about information. We had classified matter. We had divided into physical and chemical properties. We had looked at different things for that. So we're going to step all the way back to that, and we're going to work our way forward. Okay? So at the very beginning, when we classified matter, the first two things it said, when you classify matter, two different options. We had a pure substance or we had a mixture. Right? When we had a pure substance, we had two more options that we split that into. We split it into elements, compounds, and then they went on to talk about mixtures, homogeneous, heterogeneous type mixtures, solutions, things like that. Is all that ringing a bell? Okay. So this level right here, Module 2, that's where we worked at. Okay. We're not learning new stuff. We're just breaking things down more. Okay. Module 3, we started looking at only our pure substances. So Module 3, we talked about just the elements, right? An element that we learned when we were classifying pure substance, an element is a single unit. It only has one thing. It's they even said like a compound made up of a single element, a single item. Okay, so when we learned in Module 3, we learned all about the periodic table of elements. We learned that these are individual units. They all have a single identity. Their identity is controlled by which subatomic particle?
The proton.
The proton. Okay? And so we're going to be single. So it's just by itself. So we looked at the periodic table of elements, and they're just standalones. These are guys just off by themselves. They do have an identity, but they're lonely onlys, okay? Module 4, now we're moving into compounds, okay? So do you see how this is connected? We had to learn about the individual elements so that we could learn how to pair the elements together. So at this point, we are going to be looking at the compounds. It told us that a pure substance could either be an element or it could be a compound. A compound, the definition of it was two or more elements chemically joined together to make a compound with a fixed unit. It is a permanent group. they're combined with chemical bonds. Okay? So again, it goes back, they're pure substance. If these are not elements that are mixed together in different things. These are elements that have been joined that now have a new identity. All right? So this is how it connects together. So we had to learn about the individual elements first so that we could learn how they're going to work together. So when compounds are put together, there are different ways that they do that. I thought it was interesting that they address the chemical formula first. So let's see. Okay. So a chemical formula, now that we're looking at these compounds have to have a name. Right? I think it's this. Okay. The names of those compounds are chemical formulas. Right? All a chemical formula is an ingredient list. They talked about a recipe. You read about that in a book of like a recipe. If you're going to double it, then you double all the parts of it. So it's our ingredient list of what's included, a recipe. It tells us information on what is included in that group that is now a compound. Okay, this is a pure substance. It is all together by itself, but now there's more than one thing attached. So if we were to look at these, we get to use the information that we know from our periodic table of elements, and we're going to start seeing where the compounds are. So we have this one, it's CO, so we have carbon, and we have, what is that? Oxygen. So this compound includes carbon and oxygen, right? We have another one, hydrogen chloride, so we have hydrogen and chlorine. Okay, for our third one, we have, what's Na? Sodium and chlorine. And our last one is potassium and iodine. Excellent. So these are all chemical formulas. All they are doing is they are giving us information of what is included in that compound. All right. So it says on this one, it kind of went back a little bit for Module 2 if you want to reread through those. So as we get these, so how do we come up with that? Well, we start with our periodic table of elements. We have to start somewhere. If you're going to bake a cake, you have to have flour and eggs and sugar and oil. You can't just have cake mix. If you're going to shock your pool, for us, it's all off. Oh, I've got to have some borax. I've got to have some bleach. We have to have the different things to make it all work together well. If you're going to play a baseball game, you need to have a ball, a glove, a bat, and players, okay? So we are looking at the individual pieces that come together to form our entire unit to make whatever, like our game happen, our recipe happen, whatever that needs to happen, right? So we're going to start with our individual elements, and they're going to make something. Okay? So in this case, I have carbon, oxygen, and we've got carbon dioxide there. Okay? So one of the things that they talked about is they started giving you some vocabulary. The things that you need to know is that what you start with over here are going to be your reactants. So anyone have a sibling that they don't get along with? Okay, good. So sometimes your parents might say, hey, you guys can't sit next to each other at the kitchen table if you're having a rough day with each other, okay? Because they don't want you reacting together and causing a fight, right? So the things that we start with are called our reactants. Okay? They're your starting point. What you end up with is your product. So we all talk about finished product. You can think about that in manufacturing, they have the things that they come together and you create, it's like, ta-da, here's my finished product. Okay, so you're doing a science project. You guys, for this last week, you got your colored pencils, you had your paper, you had all the things, you had your knowledge, it all reacted together, and you ended up with a great final product. Okay? Other parts of our chemical equations that are important to know is that there are coefficients and there are subscripts. So coefficients are numbers in front that stand alone in front of your element. So this is a coefficient. Okay. Then you have subscripts. Sub means below. So it is below the line. It's going to sink a little bit below. So we have a subscript here. These give us different information. Again, this formula that we are working out is giving us information. So how are we gaining the information? The amount, the coefficient on the outside tells us the amount of. I need 2 baseballs for 2 different baseball players. They each need to have their own. So I need 2 of them. Okay? So our coefficient tells us how many. This is a quantity number. Our subscript is part of the identity of that element. Okay? We can change the quantity of something that we bring, right? I could choose to bring 6 cookies and the rest of you guys have none. Or I could choose to double my recipe and bring 12 cookies and we could all eat together. Okay? This is a quantity that we get to choose to bring to the table. The identity, in this case for oxygen, and I'm going to use Luke as an example, Luke is a twin. There's nothing that he can change about that ever in his life. He happened to be born with another human being. Okay? It is part of his identity. There were 2 of them that were born at the same time. No matter what he does, he can't change that about his identity. Even if I bring 2 Lukes, he's still going to be a twin for that. Does that make sense? 2 different parts. So when we are adjusting in our equations, we can always adjust how much we bring to the table. We absolutely cannot adjust the identity of the element. Okay? So you're not going to change it. And the reason that oxygen in this case has a subscript of 2 is that oxygen doesn't exist alone in nature. It's always it's paired up in that case. Does that help with those? Any questions on the vocabulary of that for the terms? Okay. So we talked about labeling the different parts of it. So then how do we go about balancing this? Okay. Balancing means you need the same on one side as you have on the other side, right? Sometimes what happens, and as we move through the module, you'll learn why things break down certain ways. You need more of one thing to balance out other things on the other side, right? So we first look at our equation and we decide, does everything that we have initially come out on the back end? Okay? So I had carbon, I added it to oxygen, and I got carbon dioxide. Here. Well, we'll start with this one because it's easy and it's balanced. They use a chart that I'm not a fan of, but I will use parts of it. Okay? So we started with carbon plus oxygen. We end with carbon dioxide. A good way is to just write down all the different elements that you have, and we're going to start comparing them. So what do I start with? I start with 1. I have 1 carbon element here. And although this does not have a coefficient, it does tell me that there are 2 of them because they come in a pair. It's a part of identity. So I have 2 oxygen there. So then we're going to look at what did we end up with. So these were our reactants. Now we're going to look at our product. Our product ended up with 1 carbon and 2 oxygen. Does everything match? Yes, it matches. That is a balanced equation. Okay. So what happens when it's not balanced? Okay, so we start out with NO2, and that's going to break up into nitrous oxide and oxygen. Okay. Again, so this tells us I start out with nitrogen dioxide. I'm going to have nitrous oxide and oxygen. Oxygen can't exist by itself, so that's why there's two of them. The identity is that it always exists as a twin in that. So the easy way that we start is we're going to put what we have as our reactants. So our reactant is here, and this is a decomposition, right? We're taking one thing, we're breaking it up into more. We ended up with more on the backside, and these are our products. Okay. So I have nitrogen and I have oxygen. I have nitrogen and I have oxygen. So how many nitrogen do I have in this first one? One. How many oxygen?
Two.
Okay. Over here, we're looking throughout the entire reaction. How many nitrogen do I have?
One.
How many oxygen do I have?
Three.
Three. I have two from here and one from there. Okay. Now, the rule is you may always add and multiply. You may always go bigger. You may not go smaller. Okay? Remember that whole matter isn't, we can't destroy it stuff. So we can make more, but we can't make less. So it is not an option to just erase an oxygen and be like, oh, I'll just get rid of one. That'll work out great. We can never take away from what we already have. However, we can grow it bigger until it balances out on the same side, right? So if we can't take away, that means I can't make my 3 a 2, but I can make any of my numbers bigger. So I could choose to make my 2 a 3, but my 2 always comes in pairs. Will I ever be able to make a 2 into a 3 if it's always going to be a paired even number? No, because this is an odd number. So that's not an option. So my option is to make my 3 bigger. Since my 2 always comes in pairs here, what's the next pair that oxygen could go to? Good job, Gavin. 4. So I want 4 oxygen. I don't want 3. I want 4 over here. How do I get 4? I need to look for a way to add 1 more. So we're going to go up to our equation and say, where can I add 1 more oxygen? So this is where our coefficients come into play. Remember, we can always multiply towards more. So I have 2 options. I can put a coefficient on my first one, or I could put a coefficient on my second one. So let's just say, right now my coefficient, if it's not seen, it's the number what? 1. So I currently have a 1. What if I changed my oxygen? Oh, I need more oxygen. I changed that to 2. Does that help me? Now I have 4, 5. That didn't help. So that's not where I should put my coefficient. I want to go up to 4. What if I change this 1 to a 2? How do I change the 1 to a 2? We are going to put a coefficient in the front of 2. Now my 2 is multiplied times every single element, and now I have 4 on this side. However, when I changed that one, it did something else.
It added 1 more nitrogen.
It now changed my nitrogen to 2. So now that I added my blue 2, I now have 2 nitrogen and 4 oxygen. So we're going to go back and we're going to compare again. Okay, so I have 1 and 2 and 2 and 4. Those almost look like duplicates of each other, right? So now I'm comparing, so first I compared forward, now I'm comparing backwards. 2 to 1, so my 1 needs to turn into a 2. How can I turn my 1 nitrogen into a 2?
Put a coefficient of 2.
Put a coefficient of 2 here. So then let's check it. 2 nitrogens gives me a 2. So I got that 2 that I wanted. But when I put the coefficient of 2 in front of the nitrogen, it also affects the oxygen. So 2 of my 2 oxygens gives me 4. Okay, now I've got 2 and 2 and 4 and 4. Did we make it where we're even? So now we are balanced. Okay? Any questions? That one make sense? I think I have another one. Okay, so let's look at this one. Okay, so we're starting with aluminum and bromine and potassium. And we're getting potassium, bromide, and aluminum. Okay, so what we start with, we're going to write down everything that we start with. How many aluminums do we have in our reactants?
1.
How many bromines?
3.
3. How many potassiums?
1.
1. Okay. Now on the, what are we ending up with on our products? How many potassiums? How many bromines? 1. How many aluminums? 1. Okay. So we're going to compare. Our aluminums look good. Our bromines do not. Our potassiums look good. Right? So what one needs to change?
You change the, you put a 3 in front of the KBr, and
Okay.
then you change the K on the left side to a 2.
Perfect. So our first thing that we want to do is we say this 3 does not match this 1. We want to turn this 1 into a 3, so we're going to do it by multiplying times 3 over here. So I need to multiply that times 3. Right? So now they'll match. But when I put the 3 coefficient, it also changed my potassium to now be a 3. So it's not a 1 anymore, it's a 3. So now we compare again. I've got 1 and 1, 3 and 3, 1 and 3. Whoops. So now we've got to go back and we've got to deal with this one. I need to turn this one into a 3. How do I turn it into a 3? I'm going to multiply times 3. Where is it at up here? Oh, I can just put a 3 right there. Did my 3 affect anything else? No, that was convenient. So now I have a 3 here. So I have 1 and 1, 3 and 3, 3 and 3. Are we all matched up? Yes, we're all matched up. Any more questions on this? Did that make sense? Yes. Their pluses and minuses for the table was a little confusing for me. These are written out steps if anyone wants to look at that. Remember the rule, you can't read that. The rule on this is that we go from where we start, write all your numbers down, and then we're going to work through each element one at a time, adjusting. Do we ever adjust our subscripts? No. You will never, ever, ever write a number in on a subscript or adjust a subscript. So we go through changing by changing coefficients and multiplying bigger. So if it starts at a 1, then we go up through 2 and then 3, the next ways. Okay. So that is how we balance the equations. So how do we form those compounds in the first place? All right. Okay. How do we form them in the first place? So how do things stick together?
Force of attraction.
There's a couple of different ways. Yep, there's different ways that they can stick together. There's actually 4 different ways that they're going to stick together. The first way is ionic bonds. The second way are covalent bonds, and then there's actually 2 different types of covalent bonds. We've got metallic bonds and hydrogen bonds. So ionic bonds are magnetic forces. Okay? We talked in the last module that when we have our nucleus and we have our electrons, our valence electrons going around the outside, you learned that group 1A is super reactive. You also learned that group 7 is super reactive. Right? what is a stable outer valence electron number? What is the stable one?
8.
8. We want to get to 8 all of the time. 8 is a happy place. 8's my favorite number. I'm totally chill. Okay? So the problem with 1 is that it's 1 away from 8. The problem with 7 is that it's 1 away from 8. So you've got this guy over here that's like, man, I've got this extra thing. If I could get rid of him, I'd be great. And then you've got these over here going, we're really close. Can someone just give us another Coke? You know, like they just need 1 more before they're going to be stable. So that is why our groups 1 and our 7 are the most reactive. We like to be paired up. Remember, each of these orbitals can hold 2 electrons. And so we like to work in pairs. Everybody's happier in a pair. I like to use a term from Nemo. It's like, do you have your exit buddy? Okay, they want to have their exit buddies so that their orbitals can be balanced. So when we're looking at this, and we're looking at ionic bonds, we have an extra electron over here, but we know that this initially, what happened between our protons and our electrons? What did we learn with our elements? The number of protons is what?
Identical.
Is equal to the number of electrons. Right, so in here I've got the number of protons is equal to my electrons. Over here I have the number of protons is also equal to my number of electrons. But they're very unstable. So if this guy in group 1 gets rid of his electron, so he loses 1, he is now stable. However, his charge is no longer equal. He now has what? More what?
Protons.
More protons. So he is positive. Okay. When we lose electrons, we become more positive. Right? So now over here, we have this guy who is really close to being stable with 7, but he really wants 8. So this guy let go of his, and it's floating around in space. And he's like, hey, come join the party. So we're going to add him over there. So now he has an extra electron. So now he has more negative things than he does positive. So his charge is now negative, but he's stable. But he has more of a negative charge. Who's played with magnets? Okay? Positive and negatives attract. So now I have a positive charged element and a negatively charged element. These 2 atoms here, they are going to be attracted to each other. That is an ionic bond. Okay? They are not attached, so if you think of it like a magnet, these are like magnets. Like a magnetic force. Okay? I said, think of it like 2 magnets that are attaching together. So they are attached solely because one is positive and the other one is negative. All right? If we decide that we're not looking at the charge of them, but they actually need to be glued together. So in this one, they're magnetic. Any one that has a positive charge is going to be attracted to one that has a negative charge. If they're not just magnetized, it's kind of stuck together like a magnet, and they're actually going to be glued together, that is called a covalent bond. Right? Oops. Once more. Okay. Covalent bonds are where you have a sharing of some electron. So you can think of it, the electron goes around both nucleuses, so you can think of it in like a figure 8 pattern. it's going to be orbiting both of them. Okay, so now versus the one that we just looked at where it has its own little identity and I've got my own identity together, but I'm magneted together, but my electrons are staying together with my own nucleus. Now when we are covalent bonds and we are gluing them together, they are going to be sharing that electron. So they talked about three different types. You have a single one and it's marked with a single line, right? A double one is marked with a double line, means they share 2 electrons. And 3 means they share 3 electrons. So when you have, remember, the goal is to be stable. That's what the whole goal is. The goal is 8 all the time. So if I have one and he just has 1 over here, and this guy has 7, they can join and he can share it, and now he's got all 8 of his and he's got all 8 of his. Okay? These tend to work better with the ones that were in the middle because they said they didn't really know what to do with it. So we've got a guy here, you know, in group 4A where he's got 4, so he needs 4 more. Well, I've got a guy over here and he's got 4. Hey, if you give me your 4 and I'll give you my 4 and we can join together and we both have 8. And so then all of those electrons will be orbiting both of those nucleuses. Those are covalent bonds. Okay? There are 2 different types of covalent bonds. When they share them equally, and those electrons are orbiting in these orbitals, and they're all going around the orbitals the same, and they're all equal, we have a balanced covalent bond. They call it equal as well. And whenever we write that, it is usually shown, like on a diagram, carbon dioxide like that, in a straight line. It means we're all balanced. Or nothing's off kilter for that. Now, if you have, so what do we know initially? Let's go back to what we learned about elements. Inside this nucleus, I have protons, right? On the outside, I have electrons. Protons are positive, electrons are negative. That means they're attracted to each other, right? My protons have a lot of mass. My protons and my neutrons give me what? The mass number there. So if I'm looking at an element that is, say, 6, I've got 6 protons, so I have 6 positive charges. And then I'm looking at an element over here that might have 18 protons. So it has 18 positive charges. Which one is going to pull on that negative charge more? 18 or 6? 18. He has more positive charges to pull. He's going to be those negative electrons are going to be attracted over here a lot more. So when you have 2 elements that are different, and we can tell usually because this is the atomic number, right? The protons give us the atomic number. So as we get bigger and further down, the elements that are further down are going to have more pull because they've got a bigger nucleus. They've got more mass in that nucleus. They're going to pull. So they're going to start hogging everything, okay? So if I put a linebacker at a table with a toddler, who's going to get all the food? The linebacker, right? He's a lot bigger. He's going to grab all the food more than the toddler is going to grab it. So as we have all of our electrons that are orbiting, and they're supposed to be orbiting equally, they might get seconds, thirds, and fourths from dinner before they get back around that other guy. All right? So then again, it might take seconds, thirds, and fourths before it gets back around the smaller guy. So our electrons are going to be orbiting around the element that has the greater positive charge, and what it does is it throws it off kilter. And those are called polar bonds. Because what it does is When more electrons are over here, electrons have what kind of charge?
Negative.
A negative charge. So I've got more electrons hanging out over here, so this side is negative. I have less electrons hanging out over here, so this proton center has a bigger charge, so this side ends up positive. So now my entire compound is a little off kilter. It has a negative side and a positive side. So if I bring some other compound over here that's negative, is it going to want to attach over on the right, or is it want to attach over on the left? It's going to want to attach here to the right. It's not going to want to come and attach on this side because this side is more negative. Okay, so polar bonds help things orient themselves in a certain way where it might be more attractive on one side and less attractive on another side. Does that make sense? Okay, so they are unequally shared. How are we on time? Oh, right at it. I got about 4 minutes. Okay. So then the other bonds are metallic bonds. We can think of those in the same thing. Why would metals be a certain type of bond? Why are they going to conduct energy more and move those electrons? Electricity is actually the movement of electrons. They happen to have a whole lot of the same words in it. So let's think about metals. Metals are usually that group 1A, right? 1, 2, we go from metals to nonmetals on the periodic table of elements. So our 1A are definitely all metals. As we work through the metals, what did we know about 1A? They all have how many valence electrons? 1. That's it. So they want to get rid of that guy. They're not stable. Our metals are not stable. They're wanting to get rid of that electron. And so they're going to pass it off to somebody. Well, as soon as they pass off their electron to someone, they are now positively charged, right? Well, they come up against the exact same element that still has his electron, and this guy is more negative now, and so they're like, oops, I'm kind of attached to you. I'm drawn to you. Well, then he gets rid of his electron, and now he's negative, and another guy comes along that's exactly the same, so these could all be hydrogen atoms. And you're like, oh, well, you're more positive than I am negative, so I'm going to be positive. You're more negative now because you've got electrons, so I'm going to be attached to you. So they're going to be attracted across, and then he'll drop his. And so that is why they're moving them along. So metals have a certain type of bond just because they are constantly trying to get rid of their electrons. So they're constantly moving between equal and positive, and so then the other one is more negative, and they're pulling on those electrons, so it's moving it along. Does that make sense? Okay. The third one is a hydrogen bond. Hydrogen is special because hydrogen is that group 1A, that very first one. It's the one that always wants to get rid of his one single electron. That's all he's got. So if he can get rid of it, man, that would be great. So when we have hydrogen, specifically with hydrogen bonding, it's usually in relation to water. Because water is a covalent bond. We have hydrogen and oxygen. We have 2 oxygens. They're covalent, but it's polar. They're not equal. They don't line up on the same side. So we see that by how we also write it. It is not written right in order like that. It is actually kind of like, kind of like rabbit ears for it. So as water is grouped together, we have a positive side and we have a negative side because they are holding more of the electrons. So we've got a polar bond in a unit here. So hydrogen bonds are the specific bonds that are caused by atoms that have water in it. Okay? So if they're asking, does this compound participate in hydrogen bonding? If it has hydrogen in it, but it does not have oxygen in it, it will not be a hydrogen bonder in the way that they're asking you here. Okay? So you're looking for hydrogen and oxygen because when those bond together, they form a polar unit with water.